about time to start. This week we're honored to have Dr. Chen Wei from Genomics Research Center in Academia Sinica to come here to share with us his very excellent research in his past few years. So let me just introduce briefly about his academic research history. So he obtained a bachelor and master degree from National Taiwan University Department of Chemistry and under Professor Mo Zhongyan. And after that, he went to UCLA as a PhD student. And after that, briefly as a postdoc fellow. And after that, he moved to Boston in Harvard Medical School for postdoc fellow for 4 years. And after that, he came back to Taiwan during Academia Sinica. And he has a very excellent publication record. So as far as I know, until today, he has 25 first author or corresponding author papers, and a lot of them are published in very prestigious journals, including Nature Nanotechnology, Nature Reviews Cardiology, Nature Communications, JACS, Angulata, Matter, Nature Com, and many more. So let's welcome his excellent research. Thank you.
Okay, thank you so much for your kind introduction. So today I'm really happy to be here and present my previous work about nanomedicine and biomaterials for drug delivery and disease therapy. So first of all, I want to declare there's no conflict of interest of my talk. So it's just a fresh refresh of my background, and so as Professor Lin said, I got my bachelor and master degree in chemistry department, National Taiwan University, in Professor Dong Mo's lab, and then I moved to UCLA for my PhD study, and after that I moved to Boston for my postdoc research under the supervision of Mr. Rasa and Professor Wei Tao. And very fortunately, last year I was able to come back to Taiwan and then join Genomics Research Center as an assistant research fellow. Okay, so here I'd like to use one slide to summarize my PhD work at UCLA. So basically, my PhD research mainly focused on using mesoporous silica nanoparticles as drug carrier and then control the drug release from these nanoparticles. So specifically, we modify many types of surface molecules to control the cargo release. For example, we modify the thermal responsive molecules on the particle surface, and we can also modify the ultrasound responsive gatekeeper on the particle surface. So once we apply like heat or like ultrasound, we can control the drug release from the carriers, and then to be able to enhance their drug efficacy and then reduce their side effect. And also we can co-load chaperone molecules to help the drug loading and release of auto-insertable drug from the nanoparticles. And in addition to drug delivery, we also use these nanoparticles as a template to template the J aggregate of near-infrared emission molecules to establish an entire new imaging agent for severe imaging. And in addition to all this research, we also have a review paper published in Chemical Research to summarize our work about how we modify these nanoparticles to control the cargo release to be able to enhance the drug therapeutic efficacy. Okay, so after finishing my PhD study, I moved to Boston, and this is about the transition. So I like to mention about this transition. So basically, this is the physical transition from Los Angeles to Boston. So usually people just fly there, right? Just from Los Angeles to Boston, and it's about like 6 hours flight. But unfortunately, this is during the COVID-19 pandemic. So we finally decided to drive there. So because we do experiments, so we have to know the data. This is the data. So basically the distance is about like more than 5,000 kilometers. And we took 8 days. And then it's, of course, we crossed 13 different states. And of course, it's 3 hours time zone, 3 hours difference in time zone. And in addition to that, and before I start from Los Angeles, the temperature is about 30 degrees. But after I got Boston, the temperature dropped to 30 degrees. So it's really different. So because this is during the pandemic, this COVID-19 pandemic. And this is my postdoc lab. So basically I have two advisors. One is my big boss, is Omni Barraza. And the other one is Professor Wei Tao. And I have two postdoc advisors. And actually they are also their postdoc advisors are Robert Langer. As you probably know, he is one of the very, very famous professor in the field of biomaterials and drug delivery. And he's a professor in MIT, and actually he's a co-founder of Moderna. All right, so here I'd like to introduce a little bit about my previous research and about the materials, about the nanoparticles, and about how we formulate these nanoparticles. So basically our materials, our particle includes like 2D materials, polymeric nanoparticles, and lipid nanoparticles, or inorganic, organic hybrid nanoparticles. And we also play some like biomaterials, bio or micromaterials, such as hydrogels, or engineered cells, or engineered microalgae. And of course, we have to, because we focus on developing like new delivery system, the delivery drugs. So this is our drugs. This includes messenger RNA, siRNA, small molecule drugs, proteins, and bioactive molecules. So the primary purpose of our study is to use our nanomaterials to carry, to stabilize, to deliver all these molecules to the disease site. And the purpose is to enhance the therapeutic efficacy and reduce the side effect of all these drugs. And during our development, we also discovered, wow, this particle itself not only serve as a carrier, these nanomaterials can also function as the therapeutics themselves. I will talk about it later. And because we focus on drug delivery and for disease therapy, so this is our disease model. In our case, in my past research and also in the future research, we will focus on like cancer therapy, cardiovascular disease therapy, and inflammatory disease therapy. So let's talk about the cancer therapy first. So this is my first work when I was in Boston. So at that time, because that is during the pandemic, so I was just every day just sit at home and then think about what I have to do during that postdoc research. So I just took out my elemental table and then just periodical table, and then wow, this thing is really fancy element for me, because at that time the 2D materials like mono element materials quite important, it's quite interesting. So I just took this one as a first example. So basically we use a method called the liquid phase exfoliation method to exfoliate the tin powder to make the tin based nano sheet, or like a staining based nano sheet. And we can also modify these particles with like a PEG, these polymeric materials, to make these particles more stable in the biological system. And the primary reason for like using like 2D materials is because these 2D materials has a very high surface area. So we can use this high surface area to carry the drugs. For example, here we use a model drug, a model anti-cancer drug called beta-alanine. So basically this drug is very hydrophobic, it's very water insoluble. So we can use our materials to enhance the water dispersibility of the water insoluble drug, to be able to increase the drug bioavailability to the tumor cells. So here we finally discovered, because this particle, this material is a semiconductor. So this semiconductor means that once we use some like energy to activate the materials, these materials can have like electron and hole pair separation, and then further react with the surrounding water and oxygen molecule to produce the cytotoxic singular oxygen and hydroxyl radical. So these alloys can be used to like kill tumor cells. And this is the first discovery of this type of new materials for like use ultrasound mediate sonar dynamic therapy. And also because these materials, we can also use like a near infrared laser to irradiate this material to enhance the temperature of the solution. So we can use near infrared to irradiate the materials to increase the local temperature and then kill the tumor cell. And the third function is because, as I mentioned, this is two-dimensional materials, so we can use these materials as drug carrier and then to deliver the anti-tumor drug. So we can just use one material for like 3 different functions, trimodal cancer therapy. And of course, we use different molecular probe to validate our finding. First of all, we use DPPA and the TMB, these 2 type of small molecules to validate our particle can really generate singular oxygen and hydroxy radical under the ultrasound activation. And as I said, because the primary mechanism of this material is because this is a 2-dimensional semiconductor, so we can use this ultrasound energy to activate the electron hole pair separation and then produce the singular oxygen and hydroxy radical, this kind of cytotoxic reagent for tumor cells. And of course, we have to try if our materials can really do something in the animal model first, right? So here we establish a tumor mouse model, and this is the tumor tissue section. As you can see here, once we inject our nanoparticle to the tumor region and then use ultrasound to trigger a tumor, we can see that the our expression is much higher than the control group. And here, if we use near-infrared to irradiate the tumor tissues, we can see the temperature abruptly increased, and the temperature is high enough to kill the tumor cells. And of course, we use tumor growth curve to validate our finding. And this group is we inject our drug-loaded nanoparticles, and we apply the ultrasound and apply the near-infrared. As you can see here, the tumor growth can significantly drop to almost zero compared with the control groups. So this study means that we can use like 1 particles and then use ultrasound, use near-infrared to irradiate the tumor and then achieve like trimodal combination cancer therapy to have the synergistic anti-tumor efficacy. Okay, so after finishing that study, we were wondering if our nanoparticle can do something to the tumor microenvironment, because in the tumor, it's not only about the tumor cells, but it's also about the tumor microenvironment. So in the tumor microenvironment, there are many types of immune cells, such as macrophage and T cell and dendritic cell and so on. So here we were wondering if our particle can, or our drug can activate or to manipulate the macrophage. Because as you probably know, in the tumor microenvironment, the macrophage, they are like M2-like macrophage. This is like pro-tumor macrophage. And if we can manipulate or like modulate the macrophage to M1-like, this kind of anti-tumor macrophage, wow, that was wonderful, right? So we just tried this experiment. And I still remember one day it's very late in the night, my 2 undergrads told me, wow, when we incubate the macrophage with our nanoparticles and drug, we are not able to detect the IL-10 signal. IL-10 is actually a very important cytokine for the macrophage. And because my student told me, well, we couldn't do that. And I was like, well, you guys screw up experiment again. So I just tried to do this experiment. And wow, it's really interesting because we can really use our drug and the particles to manipulate and modulate macrophage, to manipulate, to polarize the macrophage from M2-like to M1-like macrophage. So because we also study some underlying mechanism, and we finally discovered because our materials and the drug can slightly increase the ROS level of macrophage, and then this increase can polarize the macrophage from M2-like to M1-like. And eventually, this M1-like macrophage can participate in the anti-tumor immunity, and then combine with our chemo drug, like beta-alanine, to achieve chemo-immunocancer therapy. So this is our finding. So to validate our individual findings, we use animal model to try to see if our particle can really modulate the tumor microenvironment and also reduce the tumor growth curve. And here we use a B16. This is melanoma tumor growth curve. So as you can see, when we inject the nanoparticle itself or inject the drug itself, we can have like moderate tumor inhibition curve. But once we inject the drug-loaded nanoparticles, we can much decrease the tumor growth curve and compare with the same group. And we also harvest the residual tumors and then analyze the population of the immune cells, just like M1-like and M2-like macrophage. And surprisingly, to our surprise, in the tumor model we also discovered the M1-like macrophage can also increase, and the M2-like this anti-tumor pro-tumor macrophage decrease. So this data showing, as you can see, this data show that our materials can modulate to control the tumor microenvironment to enhance the macrophage to control or to modulate the macrophage population and achieve the chemoimmunotherapy. And as I mentioned, in the tumor microenvironment, it's not only about the tumor cells, not only about the macrophage, but it's also about the whole tumor microenvironment. As you probably know, in the most of the solid tumors, there are stroma barrier surrounding in the tumors, and this barrier would impede the infiltration of the CD4 and the CD8 or dendritic cell, this kind of anti-tumor immune cells. So we are wondering if we can use our materials or use our nanoparticle to try to use their anti-tumor function and then to modulate this stroma barrier to break this stroma barrier and then to enhance the infiltration of CD4, CD8, this kind of anti-tumor immune cells. So here we use a materials called tin sulfide nanoparticles, and actually this nanoparticle is very small. It's about like 20 nanometers. And this particle is also semiconductor. So as I mentioned, the semiconductor, we can use this property to use ultrasound to activate these materials, and then these materials can generate electron hole pairs and then react with the surrounding water and oxygen molecule to generate cytotoxic ROS. Also, these materials we discovered, this particle has a very mild photothermal efficacy. Well, this temperature is really high enough to denature the surrounding stroma barrier, as I mentioned, because in the surrounding stroma barrier, there are like fibroblasts and the collagen area. So we can use the mild photothermal effect to denature this stroma barrier and then to increase the infiltration of more CD8, CD4, this kind of T cell. And to validate our finding here, we also use 41. This is a mouse tumor model to validate our findings. So as you can see, we inject our particles to the mouse through the tail vein, and then we treat the mouse with near-infrared and ultrasound. So as you can see, the group 5, this is we inject our particles and we use near-infrared to denature the surrounding stroma barrier, and then we use ultrasound as a sonor dynamic therapy to try to enhance the anti-tumor efficacy. And once we apply this treatment 2 times, as you can see the G6, this one can significantly and to reduce the tumor growth curve, as you can see here. Okay, and then we, as I mentioned, the most important element of our study is to help the infiltration of the CD4 and the CD8 T cells. So to verify our finding, we harvest our tumor, mouse tumor, and then use flow cytometry to analyze the population of these immune cells. Of course, we can have the tumor have more like CD45. This is total immune cells, and then CD3, CD4, and CD8 and CD4 cell. So this means our treatment can really activate the anti-tumor immunity by using like a near-infrared irradiance and ultrasound treatment. Okay, so and this one because most of the time when we inject the nanoparticle to the tumor regions, we also hope our particle can stay in the tumor region for like longer and then to enhance their therapeutic efficacy. So and try to achieve this goal. Here in this study, we design and establish a new type of particles. It's called iron thickening self-assembly nanoparticles. And because iron-2 can have like a chemodynamic theory, just like Fenton reaction. Fenton reaction can produce the cytotoxic hydroxyl radical to kill tumor cells. So we incorporate iron-2 here. And then on the particle surface, we can also modify like a bioadhesive molecule like aldehyde, because aldehyde can react with the amine group to have like covalent bond. So we modify the aldehyde group on the particle surface to enhance their bioadhesive property to try to prolong the particle stay in the tumor region. And of course, on the particle outer surface, we also modify the model antigen called OVA, because we can also use this particle to carry model antigen and then try to activate the anti-tumor immunity, because this model antigen can finally release from the particle and then be uptake by the dendritic cells and then activate the anti-tumor immunity. So this study just we published in JACS, and we try to just establish these nanomaterials, try to address the challenge of like particle state in the tumor. And then the last study about the anti-tumor therapy is this one is trying to address very critical problems of PROTAC delivery. So long story short, the PROTAC is a small molecules. This is actually a bifunctional molecules, and one end of the PROTAC can bind to the protein of interest, and the other end is the molecule can bind the lipid ligase. So once these molecules can just pull these two different components together, the ubiquitinase can proteolyze the protein of interest, and then finally degrade the protein. So in the most of the disease, the oncoprotein or like disease protein is play very important role. But most of the protein probably just we don't have like proper drug. So the PROTAC technology is very, very important for this undruggable disease. So here, but one of the limitation of one of the challenge of PROTAC is the water solubility is very low. So the PROTAC cannot be dissolved in the water, cannot be delivered to the disease area, for example, tumor area. And also the PROTAC cannot penetrate the cell membrane. So once the PROTAC cannot penetrate the cell membrane, it won't be used, right? So try to address this challenge. We use a polymeric nanoparticle called this is a PDS8, and this is actually a glutathione responsive nanoparticle, and we can use these materials to carry a PROTAC called ARV771 to stabilize or to deliver this PROTAC to the tumor area, and then finally release this PROTAC into the tumor cells. And actually, this ARV771 is act on the oncoprotein called BRP4 and the c-MYC, this kind of oncoprotein. So eventually, we can use this technology, this PROTAC nanotechnology to deliver protein molecules and then release the PROTAC, and finally act on the BRP4 oncoprotein and hydrolyze and degrade the oncoprotein for anti-tumor therapy. So as you can see, we also use animal model to validate our finding. Here is this tumor growth curve. Once we inject the PROTAC loaded nanoparticle to the mouse tumor, to the mouse model tumor, we can see here the tumor growth, and we can see the big difference compared with the control and the control particle growth. Okay, so this section is about the tumor therapy, and because in addition to the like cancer and the tumor, the other very important disease is cardiovascular disease. And the cardiovascular disease, one of the most important cardiovascular diseases is atherosclerosis. And here I will talk about how we use nanoparticle to modulate the macrophage and to treat the atherosclerosis. And here I would like to use one slide to, this is our published in Nature Reviews Cardiology paper to introduce the atherosclerosis. So basically atherosclerosis, we call it 动脉粥状硬化 or 动脉粥样硬化. So basically this is a vascular disease. And how this disease happens is just like this is our vessel, and this is endothelial cell. So when like people like they have some bad habit like smoke, or like they have very high level of low density lipoprotein cholesterol, this is bad cholesterol. This cholesterol may activate the endothelial cell to make the endothelial cell express like ICAN and DCAN, this kind of adhesion molecules. And this adhesion molecule will attract the monocyte, and the monocyte will just migrate to the subendothelial region to here, and then differentiate to macrophage, which is an immune cell. And the macrophage may uptake more LDLC, like low density lipoprotein cholesterol, and then finally it will become foam cell and dead cells. And during this process, the macrophage, they will secrete more pro-inflammatory cytokine and RS. And the pro-inflammatory cytokine, they will attract more monocyte to infiltrate into this region. And eventually, in the vessel, you will just like this. This is like called plaque. And in this plaque area is contained a lot of dead cells, macrophage, and cholesterol. And eventually, once the plaque is larger, once this plaque is very, very large, the endothelial cell cannot just contain or just maintain the surface, and then finally it just erupt to the blood. and this will result in like myocardial infarction and a stroke. So basically, atherosclerosis this is very important and very urgent disease to be treated. And so apparently, as you can see, a macrophage this is a very important therapeutic target for this disease treatment. So in the clinics, there are like several treatment strategies. One is called like low density protein cholesterol lowering drug. Just as I mentioned, the low density protein cholesterol. This is bad cholesterol. This is very important cholesterol. So most of the time, people just if the patient they are diagnosed with like a very high level of LDL-C, they will just the doctor may just giving like statin. This is LDL-C lowering drugs, or like another drug is called PCSK9 inhibitor. And so basically these two inhibitors they are just monoclonal antibody, and so they can neutralize the PCSK9. This is a very important protein in the liver which can metabolize the LDL-C. So this one is also these two are also the drugs in clinical use. And the other drug is called PCSK9 siRNA. So basically this drug is very important and very highly recognized because this drug this just approved 2 years ago, and this one shot can just last long like for like 6 months. So people just if people have like a high LDL-C level, so just take this shot like every 6 months. But this one is very expensive. One shot is about like $6,000 US. So this drug is very expensive. And so because as I mentioned, this disease is called inflammatory vascular disease. So in recent years, people just shift this therapeutic strategy from LDL-C lowering to anti-inflammatory drugs. So for example, in the past, people use like anti-IL-1 beta monoclonal antibody. Actually, this IL-1 beta this is a pro-inflammatory cytokine. So if we can neutralize the IL-1 beta, wow, that's really wonderful, right? So this drug they pass phase 1, phase 2 trial, but in the phase 3 trials they failed. And this is mainly because this IL-1 beta. This is because this one they have very strong side effect like bacterial infection. Okay, and the other drug is called methotrexate, and this drug is also an anti-inflammatory drug. This is a small molecule drug, and again they pass phase 1, phase 2, but in the phase 3 trials they failed. And because they systemically deliver this drug to the patient, and the bioavailability of this drug is not really high, so finally the efficacy is not really good. And the other drug is called trypsin. This one is also a very famous drug that can be used to treat inflammatory disease. And this one is actually developed by this company, Edgewise Pharma. Actually, this one is a family-run, family-owned company, not like pharma. Okay, and this one they passed the phase 1, phase 2, and very fortunately they passed phase 3 clinical trial, and then this one is already approved. But however, their efficacy is not really that high. So all these trials, the therapeutic implication of all these trials suggests that if we can develop something like target delivery of anti-inflammatory drug, this one can not only increase the therapeutic efficacy of the anti-inflammatory drugs, but also reduce their side effect. So for this purpose here, we developed a new type of materials called black phosphorus nanosheet. As you can see, this is a two-dimensional materials. So as I just mentioned, the two-dimensional materials is because this one have a very high surface area, so this particle can be used to carry and to deliver a lot of drugs. And also we can use this particle, we can modify this nanosheet. We can also modify the nanosheet surface with targeting ligand. For example, because as I mentioned, this is drug for like target macrophage, right? So we can modify the particle surface with STP peptide, try to enhance our particle accumulation in the macrophage area, and then to be able to be uptake by the macrophage. And also because, as I mentioned, this is black phosphorus, and black phosphorus can react with oxygen, right? Because this one is, their reaction very quick. So these materials, these PPNs can scavenge ROS, such as single oxygen, can scavenge hydroxyl radical and the superoxide anion. This kind of ROS overexpressed in the plaque area. So we can use our materials to scavenge the overexpressed ROS and then try to reduce the ROS expression in the plaque area. And eventually, the particle can degrade into like phosphate ions. So if you have like culture experiments, the phosphate ion is the main component in our PBS solution. So eventually, this particle can be degraded to the non-toxic phosphate ions, and then to be able to degrade from our body. And during this degradation process, the drug RBD1 can be released from the nanoparticle and eventually act on the macrophage, and then to produce the anti-inflammatory efficacy. And actually, RBD1, this is the like pro-resolving or anti-inflammatory drug to be able to can be used to reduce the inflammation from the macrophage. So actually, this is one of our recent study. Try to use the nanotechnology delivery platform and to deliver the water insoluble pro-resolving mediator like this one. And we can also modify the targeting ligand on the particle surface and try to enhance their accumulation and targeting efficacy by the macrophage, and then try to treat this disease. And this is the basic characterization of our materials. As you can see here, the particle size is about like 100 to 200 nanometers, and the thickness of the black phosphorus nanosheet is about 15 nanometers. Of course, because we modify the particle surface with PEG, so the particle has very good colloidal stability in the PBS and in the cell culture medium. And as I mentioned, this nanoparticle, these materials can be used to scavenge ROS, like hydroxyl radical and the superoxide anion, try to reduce the ROS level in the plaque area. And we also see that the RBD1, the small molecule drug, can be released from the particle surface and then have a controlled release behavior here. And try to validate our finding here, we also use raw macrophage as a model macrophage, try to see if our particle or our drug can really reduce the ROS levels in the macrophage. So here we use LPS to activate the macrophage first, and then we incubate the macrophage with different type of formulation, includes particle, drug, and drug-loaded particle, and drug-loaded particle with targeting ligand. And of course, these materials, this group have the highest ROS scavenger properties, and then compare, as you can see, compare with the model group, this one have the highest ROS scavenger efficacy. And we also collect the medium, the cell medium, and then try to analyze the cytokines secreted from the macrophage. As you can see here, this all these cytokines demonstrate validate that our materials can significantly reduce the secretion level like TNF alpha, IL-1 beta, and IL-6. All these pro-inflammatory cytokines can be significantly decreased or reduced. And after in vitro model, we also use animal model try to see if our particle can really treat, to be able to use to treat the atherosclerosis. So here we have like apolipoprotein E deficient mice, and we fed these mice with high fat diet, just like have a lot of fat, sugar, and cholesterol, and try to make these mouse have the plaque in their vessel. And then after we got the atherosclerosis mouse, we fed the mice. We use an IV injection of our nanoparticle to the mouse. And then after like 12 hours, after 12 weeks of treatment, we collect, we isolate, we harvest the entire aorta, like zygoma, and then try to use oral staining to see the plaque area, the plaque size. As you can see here, the red signal means the plaque. So as you can see here, after our treatment, we can significantly reduce the plaque area compared with the study groups. And we also use like a tissue staining section to validate our finding to validate our nanoparticle can really reduce the plaque area in the aortic root. And try to study the underlying mechanism. We also section the aortic root and use ROS staining and immunofluorescence staining, and then validate, well, our materials can really reduce the ROS level, and then reduce the pro-inflammatory cytokine level, and increase the anti-inflammatory cytokine like IL-10 level. Okay, so this is about one of our study about how we use nanoparticles or nanomaterials treatment strategy, especially target the nanoparticle to try to increase the bioavailability and the therapeutic efficacy of our nanoparticles. And as I mentioned, because IL-10 is an anti-inflammatory cytokine, right? Or like a pro-resolving cytokine. So we are thinking if we can use mRNA technology to try to address the current delivery challenge of for the atherosclerosis treatment. So here we use IL-10 messenger RNA, and we use our ionizable lipid called GLC14, because messenger RNA, this is very promising, and probably everybody knows this messenger RNA. But one of the difficult for this molecule is because this one the stability is very low. So we have to use something to carry to stabilize the messenger RNA and then deliver the messenger RNA to the plaque area and then to the macrophage. So here we use a polymer called HA polymer, try to stabilize the entire complex, and then on the particle surface we can also modify the targeting ligand. So basically this is a dual targeting function, and one of the targeting is the KC peptide can enhance the particle accumulation in the collagen 4 area surrounded in the plaque area. And HA nanoparticle is actually a targeting polymer for the macrophage. So this is the first dual targeting nanoparticles for the delivery of IL-10 messenger RNA. Try to enhance the IL-10 messenger RNA bioavailability to the plaque area and to the macrophage area, and then make macrophage try to translate IL-10 messenger RNA and then secrete more IL-10 messenger RNA, try to enhance their pro-resolving function. And this one, actually this study finally we also isolate the entire aorta and the aortic root, and then use the tissue section to validate our design or our materials can really reduce the plaque area, as you can see here. Okay, so in addition to IL-10 messenger, in addition to IL-10 messenger RNA, and in the plaque area, because as I mentioned, macrophage play an important role in the disease progression, right? But in very recent study, people see that a gene called IL-5. This gene is very unique in the macrophage area, because people found this gene is overexpressed in the plaque macrophage. And once this gene is overexpressed, the ability of the macrophage to remove the surrounding dead cell, this ability will be diminished, will be decreased. And try to address this challenge. And actually, currently there is no drug targeting these gene molecules. So here we try to see if we can use siRNA technology to address this very important challenge. And here as you can see here, we develop a new type of nanomaterials based on the FDA-approved PLGA nanoparticles. And on the particle surface, we also incorporate ROS responsive called thioketo function groups here. So once these nanomaterials contain the siRNA nanoparticles circulate to the plaque area and then reach the ROS expression site, this nanoparticle will break, and then eventually the siRNA can be released to the macrophage area, and then finally to knock down the siRNA expression in the plaque in the macrophage. So as you can see here, this is the IF imaging. This is staining imaging of IL-5 gene. And after injection, after the nanoparticle infiltration, our nanoparticle can really knock down the lesion area, the lesion macrophage IL-5 expression, and then reduce the plaque area, as you can see here. All right, so in addition to all this, how we use nanoparticles to deliver how we design, how we develop a new type of particles to deliver our molecules, like for resolving mediator, messenger RNA and siRNA to the plaque area, try to modulate to control the function of macrophage or control the phenotype of the macrophage. We also summarize in the past how people use nanoparticles approach strategy to address all these questions. Like people just deliver the drug to the monocyte, to macrophage, to reduce their transition or to enhance their pro-resolving function or reduce their anti-inflammation function, or try to deliver drug to enhance the macrophage efferocytosis, as I mentioned before. So all this study we provide a comprehensive summary, and we also provide our perspectives about how this field will advance in the next page. Okay, in addition to this one, we also summarized in the past year how people use chemically modified approach to modify the RNA molecules, try to make RNA more have higher therapeutic efficacy and reduce their side effect. For example, we summarize like ASO, aptamer, siRNA, messenger RNA, and so on. And we also summarize or to just provide perspective about how people use nanoparticle formulations approach, try to deliver all these RNA molecules to try to deliver this molecule to the disease area, to the right organ, to the right disease, to the right organ, to the right cells, and then try to do the some right thing and reduce the side effect. Okay, so this is about how we use our material design to address the current challenge about the atherosclerosis, this kind of cardiovascular disease therapy. And the final section is about like as a short section. I will talk about how we use like living materials, these different materials for inflammatory disease therapy. So this is for like colitis. Actually, this is an intestinal disease. Actually, this is intestinal inflammation treatment. So in the United States, it's about like 1 to 2% of people have this kind of disease. It's called colitis. But actually, this is no drug to treat this disease. And because this is inflammatory disease, and this is like in the intestine. So our thinking is if we can use like oral delivery, we can use like oral delivery to deliver drug to try to reduce the inflammation, especially the intestinal inflammation, right? But as you can see, probably as you know, oral delivery is the most convenient and the most patient compliance delivery strategy for all disease. However, because in the stomach, all the drug have to pass, all the drug have to stay in the stomach or pass through the stomach. But in the stomach, the pH level, pH value is very, very low. It's about 1 to 2. It's a strong acidic environment. So if we don't have like a proper carrier or proper delivery strategy for these drugs, the drug may be degraded in the strong acidic environment in the stomach, right? So here we try to use different materials called microalgae. Microalgae. This is edible, so we can eat this one. And this microalgae is micro materials, and because this material they have their surface have pore, so we can use pore to store the water-insoluble drug, just such as curcumin here. And then eventually we can use the entire formulation and then to establish a new oral delivery platform and then have the mouse to eat it. And there are different advantages of this delivery strategy. First of all, because this one, as I mentioned, this microalgae, we can use this microalgae as a protection layer or protection carrier to protect the water-insoluble drug, and then try to have the water-insoluble drug to deliver to the intestine area. And we can use this one as a non-invasive imaging because we can check. We can use the fluorescence property of these materials, so we can real-time to monitor where this materials is. Try to see how long they will stay in the stomach, how long they will stay in the intestine, and how long they will stay in the body. And we can also have, because another important property is because this shape, this is a helical shape. So this helical shape, once they pass through the stomach, they accumulate in the intestine. They will preferentially stay between the villi. This is Rongmao. So they will stay here and for the long-lasting intestinal drug release. So we also have one control group. We use like spherical microalgae, and then we found this helical shaped microalgae. They have like longer retention time in the intestine compared with the spherical microalgae. So finally, because the final advantage is because these materials is edible, so this one has a very excellent biocompatibility. So for this purpose, we just use these materials as a new oral drug delivery platform for the delivery of the water-insoluble drug, especially for the anti-inflammatory properties. So this is our model about this, the colitis model. So we just get a mouse and then use this as water to establish this mouse model. As you can see here, this once the mouse have like colitis, their intestine they will be shorter than the control group. And if we have this mouse and if we feed our nanoparticle, if we feed our microalgae, especially the drug-loaded microalgae, we can restore the length of the intestine and then try to restore their normal function. And of course, we also have a section like tissue section, try to study the underlying mechanism of the our design. So of course, we can see that on the TNF alpha, the pro-inflammatory marker is decreased, and also the IL-6, the expression also decreased. So basically, this disease model, we can use these particles for like oral delivery. We establish this entirely new oral delivery platform and try to deliver the water-insoluble drug, and then protect the drug molecules, and then help the drug molecules pass through the stomach, and then finally reach the intestine region, and then reduce to do the right thing. Okay, so the conclusion is, in my talk today, we talk about like different type of disease. We talk about how we use black phosphorus for the atherosclerosis study. So actually, black phosphorus, this one can also be used to treat other inflammatory disease, not only about the atherosclerosis, not only about the atherosclerosis cardiovascular disease. And we also talk about the staining-based nanosheet. We use these materials as serve as a trimodal combination cancer therapy. So actually, this one may be also used for other solid tumors, not only about like 41 tumor. And we also talk about tin monosulfide nanoparticles. We describe how we use these materials to destroy this stroma barrier, and use these nanomaterials, use their semiconductor properties, use ultrasound to trigger these particles to produce more RS and try to kill the tumor cells. And of course, we also discuss about polymeric nanoparticles or lipid polymer nanoparticles. Use these biocompatible particles to deliver siRNA or messenger RNA. This kind of like biomolecules try to act on the intracellular signaling pathway. And of course, we just talk about the living materials. We talk about how we use living materials to establish a new oral delivery system. And of course, all these materials because we have to carry the therapeutics, so we also have this kind of like engineered formulations. For example, we talk about how we formulate the small molecule drugs, how we use these nanoparticles to load and to deliver the immune modulating drug. And we also talk about how we use black phosphorus to deliver the bioactive lipid mediator and try to enhance the water solubility or water dispersibility of the bioactive lipid mediator. And we also talk about how we use this nanoparticle to deliver anti-inflammatory drugs and messenger RNA, siRNA, and protect, and so on. And of course, after we obtain all these formulations, we care about how these formulations act on the disease tissue. For example, tumor tissue, how these particles act on the tumor cells, how these formulations act on the tumor-associated macrophage or pro-inflammatory macrophage, or how our nanoparticles act on the tumor microenvironment and try to help the infiltration of the T cells, or how our nanomaterials carry the siRNA and the messenger RNA and act on the intracellular signaling pathway. And of course, all these formulations, we have to use the proper delivery technology to try to deliver all this formulation to the right disease, to the right organ, to the right cells, and do the right things. So we use intravenous systematic delivery. We also use in situ engineering. We also use oral delivery. Of course, we can modify the particle surface with a proper targeting ligand, like peptide or other ligand, try to enhance all these particles accumulation in the right cells. Of course, in the next session, we also talk about how we use living materials as carrier. This is entirely new. It's different from artificial nanoparticles. We use these living materials and to carry the model of drugs and try to address the current delivery challenges. Okay, so finally, I'd like to acknowledge my previous lab, my postdoc lab, and in our current lab, we also focus on delivering new type of nanomaterials. We will also try to address the current delivery technology, and we will also try to address the current challenge in like messenger RNA, siRNA delivery technology. And we will also try to use our new formulation, try to do the new applications. And we are not looking for the exceptionally multi-talent individual, but we are looking for like student and use their talent make the most of the technique. Thank you so much.
Thank you very much. We're taking questions from the audience.
Three questions.
Yes.
The first question is, I assume that the molecule that attached to the nanoparticles whose conformation is correct, therefore it has the therapy effect.
Yes.
But before you apply to the therapy, how do you know the conformation of the molecule attached to the nanoparticles is on its right side? Is the precise conformation? So this is the first question.
Okay.
And the second question is about the specificity of the nanoparticles. It sounds very exciting to use nanoparticle as a mediator to carry the effective molecule to do the therapy. But if the treatment is not specific, have you ever heard about any side effect that occur and which cause even bigger damage than the target,
Yes.
which may be mice or human beings, and become even more serious?
Yes.
Yeah, I think my third and my second and third question are about this specificity. So
Okay.
the first question is about the confirmation.
Okay.
How can you
Yes.
make sure that the confirmation is not changed?
Okay.
Thank you.
So this question is really, really important and really wonderful. So thank you for this question. And for the first question, the confirmation, because most of the time we load our drugs is on the particle surface or inside, right? And this drug is eventually they will release from the particles. So I believe the confirmation the structure they will still the same if we have the proper protection for the drug. So when the drug act on the cell environment, the molecule, the chemical structure, they will still the same before they load it in the particles. Yeah. So in terms of the confirmation, I think it should be okay. And the second question is about the specificity, right? So, so one of our purpose is to try to enhance the bioavailability of the drugs to the disease area. So the dose, of course, we have to care about the dose. The dose is in the safety range. And once they in the safety range, if we have a proper formulation, their accumulation or their bioavailability in the disease area, they will be higher compared with the free drugs. So given this, so I believe, of course, if the drug, the dose is too high, of course, they will damage something, like damage the normal organ. But if we can control the, of course, first of all, control the dose, the injection dose, or control, of course, we have to do the right formulation and then try to make the particle or materials, they can accumulate more in the disease area. So that's why we have all these designs, and we will try to have a targeting ligand and so on. And we can also use like different injection route, like inhalation or in local injection, try to enhance their availability to the right cells. Yeah, but of course, if we do like IV injection, of course, during IV injection, particle they may reach to other organs. But if the dose is like below the threshold, like toxic threshold, I think that should be okay. The body can finally just degrade or like secrete these molecules. Thank you for your question.
More questions?
我就用中文问好了。
是，Yeah。
那个 IL-10这种 interleukin 这个它们来它们都很短。用 mRNA stretch deliver 的话，有个很大的好处就是，它可以抑制产生，看起来就它的寿命很长。我不知道在你们 case 这个 mRNA 它的这个表达这个效果可以持续多久？免得一天到晚要打针。
OK，好，走，我就用中文回答。那这个，因为 IL-10的 messenger 它表达我们之前试过，它其实持续大概3天， 在 microphage 大概3天，那我们会去收集它的 cytokine，然后去侦测。那当然就是说这个 disease progression 在老鼠跟在人的 disease progression 的速度是不太一样，人的话是慢很多。所以如果我们今天即使这还有 10它3天后没有在 microphage 它没有在持续的释放，但它在整体的这个 microenvironment 的效果它还是会持续的，它不是 IL-10没打完它就没有，对，所以它但它的不能持续像一直在释放，但它已经去改善了整个 local 的 microenvironment 之后，它应该可以维持一阵子。
然后 systemic toxicity 有没有去看到？
有，这个我们有去看，把所有的 organ 包含的心脏啊、肝脏啊、肺脏啊、脾脏全部都取出来去做 tissue staining， 然后去看它的用 HE staining 去看它的 tissue 都是 normal 的，然后也确实去侦测一些血液的指标，那这些指标就我们确定，它这个 plaque 变少，它不是透过 low density protein lowering， 就是透过 anti-inflammation 的治疗效果。
OK， 谢谢。
Right. I would be interested. You have presented so many different approach, right?
Yes.
Different nanoparticle approach. Which one of them is under this phase 1, phase 2 test?
Yes. Okay. So this is very good question. This one the polymeric nanoparticle. This is more like reach phase 1 clinical trial. I can say because polymeric or lipid nanoparticle or polymeric nanoparticle. These two are like more like close to clinical the phase 1 or phase 2 clinical trials. And there are some drugs they like use polymeric like PLGA as a carrier. So I think this one be more like close to clinical trial. Yeah. And of course lipid nanoparticle. This one. And currently my lab also work on lipid nanoparticles. And this one is actually FDA approved for vaccine, but for other purpose, we still have tried to do that. Yeah.
That's under the United States, right?
Oh, lipid nanoparticle. This is my current lab.
The current lab.
Yeah.
Okay. Second question.
Yes.
You use a lot of this mouse to the test, right?
Yes.
Can you share with us how difficult it is?
How difficult? How to
to handle them? Yeah.
Well, at first it's very difficult. It's very hard to like catch or try to grab the mouse. Yeah. But I think because my background is always chemistry, but after I joined the lab, I just learned like 1 to 2 months. I think it should be okay. Yeah, it's very comfortable for me to grab the mouse. Yeah, it's not that difficult. Yeah.
Any more questions? Our students? Okay. Yeah.
One more question.
Yes.
I noticed that one strategy of your research is to embed a particular molecule within the nanoparticles, expecting that at a certain time point, it is dissolved within the cell or around the cell.
Yes.
But how can you control the efficacy or the efficiency of being dissolved? For example, if you expect it, the best timing is about 2 hours, it can reach to the target tissue or cells. But how can you control it will be certainly dissolved after 2 hours? And if now this is feasible, how you can control the dissolving efficiency? Thank you.
Okay, that's very good question. So, for example, for this study, this is I think probably this one is just you just mentioned about because this material this is like ROS responsive, or ROS degradable nanoparticles. So in the normal condition, like in the serum or in the blood, this one the stability is much higher than the particles in the plaque area. because in the plaque area, the growth expression is very high. So once these particles, these materials reach this region, the particle will degrade. Yeah, so we are not able to control, we are not able to use like external energy to control the particle degrade, but we just use the natural properties of the disease to control the particle degrade. Yeah, so this is our design. So that's why we use these growth degradable particles for our drug delivery study. Yeah, so I think this one is actually like responsive to the natural property of this disease. Of course, we can use in other case, we can use like ultrasound, we can use light or other method to try to activate the materials. Yeah, of course that is doable. Yeah, but I think it also depends on the disease, different disease scenario and different disease application. But actually this one is very, very good. Yeah, thank you so much.